the organizers of this conference for giving me this opportunity, and in particular Pujya Swamiji, who insisted to incorporate this topic, that is Higgs boson. And Professor Kagali and Pujya Swamiji have made my job simple. Almost they have described everything what I am going to present now in a nutshell. From this slide you can notice I have highlighted the name Higgs boson and I have kept Govt particle in very small letters. In fact, when the organizers approached me, almost I opposed to use the word Govt particle. But since it came from the mouth of Swamiji, Pujya Swamiji, I said let it be. Let us see what to call it, whether Govt particle or Higgs boson at the end of my talk. So before actually discussing about Higgs boson, as both the Swamiji and Professor Kagali said, so it is very important to know about the basic forces in nature. I have arranged these in a chronological order. Long back, before 1600, before Newton, we knew about only gravitational force. And people thought that there are two types of gravity: astronomical gravity and terrestrial gravity. You know that if you throw any object, it will just fall back because of the Earth's gravitational pull. Before Newton, scientists believed that this is a local phenomena and they called it as terrestrial gravity. And if you look at the celestial objects like planets, stars, etc., everything is exhibiting a rotational motion. As far as the first law of Newton is concerned, unless and until an external force is applied, the object either remains at the state of rest or it moves in a straight line. But look at the celestial objects, everything is rotating about something else. So there must be a force for this rotational motion, and they called it as astronomical gravity. People thought these two are different. But it was Newton around 1600 who unified these two, and he called it as universal law of gravity. He was the one who gave universal law of gravitation. He just said there is one gravity and it is controlled by a single equation. He gave Newton's law of gravitation. You have studied about Newton's law of gravitation. So it was Newton who unified these two, and now we know that there is only one type of gravity, and that is the one which is responsible for giving the structure for the entire universe. Similarly, the story extends for even electric and magnetic force. Before Maxwell, people thought that electricity is different from magnetism. And it was Maxwell, through his equations, famous equations, you haven't heard about Maxwell's equations, unified that and these two are same. And he called it as electromagnetic force. Now we know that we have gravitational force which is responsible for the structure of the universe, and electromagnetic force. Whenever there is charge, that is very weakest force in nature. And if you consider electromagnetic force, the basic nature is to find repulsion between the protons. Protons are positively charged particles. So there must be, as Swamiji said, there must be some other force which is fundamental again, and it is totally different from these two, and it should be stronger than the repulsive force. And they called it as strong nuclear force. That is the one which holds all these protons together inside the nucleus. Strictly speaking, that is only a residual component. Strong nuclear force actually acts between quarks. That means, gluons. The residual component acts between the protons. So that means the actual strength is even more than that. That is why the name strong nuclear force. That is the strongest force that you find in nature. But in addition to these three, next one please, you require one more force to explain decay process. You know that This strong nuclear force is the strongest force, but still certain nuclei will undergo decay. You have heard about radioactivity, alpha decay, beta decay, so all these things. How to explain these decay mechanisms? So we require one more force, that is called as weak nuclear force. It is called as weak nuclear force because it acts within the nucleus. Among the nuclear forces, that is weak. Strictly speaking, that is not weak as compared to the other forces. Gravitational force is the weakest force in nature. Out of these four forces, next one. Yeah, actually this slide is to say how force act between particles. I have just given an example here. We know that we call about attraction and repulsion. Say for example, if you bring two light charges close by, they repel each other. Or if you bring two light poles nearby, they repel each other. Even though there is no physical contact, there will be repulsion. How this can take place? There is no physical contact. You bring one magnet near the other magnet, you either find attraction or repulsion. Even though there is no physical contact between them, this attraction or repulsion happens. How this is possible? Electrodynamics gives the answer for this. From the electrodynamics, we know that it is through the exchange of some virtual particles called as photons. We call them as virtual photons. And that is called as exchange theory of forces. Similarly, we can expect for all other forces. Next one, please. Actually, from this, this gives the summary of the story which is said by Swamiji and Professor Kagali. You can notice that we have four forces. Gravity is the weakest one and strong nuclear force is the strongest one. Suppose if I assign the strength of this strong nuclear force as 1, and you can notice that gravity is 10 power 39 times weaker than the strong nuclear force. Just look at this. But each of them, each forces, they have their own role in the universe. As I said, gravity is the one which is responsible for the entire structure of the universe. But to explain the structure of a proton, you require strong nuclear force. They have their own role in the universe. Next one, please. Now let me go deeper into the nucleus, because the main topic is Higgs boson. I want to talk about the Higgs boson. So if you get into the nucleus, you will find so many particles. Or if you take atom as an example, you have electrons. At least BSc students know that there are protons and neutrons inside the nucleus. But after the invention of particle accelerators, they have invented many particles. And a better classification is required for better understanding. That is why people have classified these particles. And we have leptons and hadrons. For this classification, you cannot use gravitational force. Gravitational force is very weak force, but these particles do have very small masses. You cannot use gravity for this classification. You cannot use even electromagnetic force, which we described in the last slide, because most of the particles are neutral particles. And you know that the electromagnetic force comes into picture only if there is charge. So those two forces, gravitational force and electromagnetic force, you cannot use for classification of these particles. So people used strong nuclear force and weak nuclear force, and those particles which are affected by weak nuclear force, they are called as leptons, and the rest of the particles are called as hadrons. As Kagali sir said in the morning, so we have 6 varieties, 6 lepton flavors. We have electron, muon, tauan, and 3 neutrinos corresponding to them. So there are lepton flavors. And in hadrons, some of them are fermions and some of them are bosons, depending on the spin as the criteria. So they can be further classified into mesons and baryons. Mesons are basically spin zero, they are bosons. Whereas baryons, they are fermions. They obey Fermi-Dirac statistics. And even with respect to quark composition, they are different. They are not fundamental. They consist of so many other particles, they are called as quarks. Baryons are basically quark triplets. That means they are made out of 3 quarks. And mesons, they are quark doublets. They consist of 2 quarks. But this quarks again obeys Fermi-Dirac statistics, that means they are fermions. And when you consider 3 quarks describing a particle, again Fermi, Pauli's exclusion principle will come there. So to escape from this, mathematical formulation says they should come in 3 colors. Color is a quantum number, it has nothing to do with the colors that we find in day-to-day life. So we have red, green and blue, primary colors. So that the quark containing particle will be white. So with that analogy they use these 3 quarks. And again there are 6 varieties. We have up quark, down quark, charm quark, strange quark, top quark and bottom quark. So they are just names. And all these 6 quarks, they come in 3 colors. So that is 6 into 3, 18. And each quark has an anti-quark. So 18 into 2, 36. So there are 36 varieties you can say. And any 3 combinations of this will produce a baryon. And any 2 combination will produce a meson. So just imagine 36C2, you can use D bar with a normalization also can produce a particle. That means within the nucleus itself we find more than 10,000 particles. So that particle physics is really complex one. So this is about classification of particles. Next one. And this is the periodic table of elementary particles. Kagali sir was mentioning about the first generation quarks, leptons, etc. So you can notice here we have 6 flavors. So I mentioned that up quark and down quarks. The first column, if you consider the first column, that is the one which is used to describe the ordinary matter. In the ordinary matter, find protons, neutrons inside the nucleus and electrons around it. So protons, if you consider, they consist of 3 quarks. There are 2 up quarks and 1 down quarks. You can notice that all those things comes in the first column. And you have electrons around it in the nucleus. That means to describe ordinary matter, you require first generation quarks and leptons. You have electrons, for example, beta decay, if you consider, you require electron and neutrino to describe this. So that is the first generation. If you go for higher energy, you get second generation. More high energy, you get third generation. But as I said, I told you about the exchange nature of these forces. So every force is mediated by the exchange particles, and the exchange particles are the gauge bosons. So that is kept in the last one. But this is an incomplete periodic table. There are a lot of information, so that is given there in that slide. So it has mass. Mass increases if you move from left to right, and the top quark has maximum mass. Okay. So this is about the periodic table of elementary particles, but something is missing. So we will discuss that later. Next one. So at this stage, so you know that universe started very long back. So with an explosion, that is Big Bang explosion. Now we are at this stage. So at this stage, the universe temperature is about 2.7 Kelvin. The average temperature of the universe is about 2.7 Kelvin. So now we have these 4 forces. Whether this was the same even earlier at the time of Big Bang theory. No, it is not the case, because people have proved that in 1964 they observed Salam, Steven Wheeler and Blanchot. They proved that at about energy 100 GeV, or if you reach the temperature of the order of 10 power 15 Kelvin, you don't find any difference between electromagnetic force and weak force. They get unified, and they call that unified force as electroweak force, and for that work, in fact, they awarded Nobel Prize. And people have gone even beyond that. Suppose the energy is of the order of 10 power 14 GeV, or if the temperature is of the order of 10 power 27 Kelvin, you will never find difference between unified. And in fact, that unified force is called as grand unified force. People have got, theoretically they prove that if the energy is of the order of 10 power 19 GeV, or temperature is of the order of 10 power 32 Kelvin, it is possible to unify even this grand unified force with gravity. And that is called a super grand unified force. And that was the situation which was there at the time of Big Bang. That means this is already tested by nature. At the time of Big Bang, all these four forces were unified. We had one single force. But you know that the universe is expanding, the temperature is getting reduced, and from there all these forces were frozen out. They got separated. At this stage, we have this situation. We have four fundamental forces that is described in the nature. But the interesting thing is the electroweak force. Why this symmetry breaking phenomena happens? To answer this question, you require Higgs boson. Next one, please. This electroweak force unification, actually that postulated the existence of the Higgs particle. As I said, at about 100 GeV, you don't find difference between electromagnetic force and weak force. They are identical. They are governed by the same equation. But if the temperature is reduced, you will see that they get separated, and there will be asymmetry between these two. So that is called as breaking of symmetry. And breaking of symmetry can be explained by using this quantum chromodynamics. So maybe in the next slide I will take up this. And there actually they said, for this mechanism you require a particle, and they named it as Higgs boson because that was theorized by Peter Higgs and Englert and Govt. To find this Higgs boson, so they constructed several labs around the world. So one is Fermi Lab at Reliance, USA, and Large Hadron Collider at some lab. And these were basically dedicated for the discovery of this particle. And the discovery is basically to answer two important questions. One is symmetry breaking mechanism, and what actually giving the mass for all these particles, eight particles. They should be, theoretically speaking, they should be massless. But W and Z bosons, photon of course that doesn't have mass. W and Z bosons do have mass. What is actually giving mass for these exchange particles, that is W and Z bosons? To answer these questions, this particle is very much required. So they started hunting for these particles and they constructed various labs, and the discovery started. Next one. And actually this is the potential, the nature of the potential that they use to describe Higgs mechanism. You can notice that any kind of fluctuation may destroy this symmetry, and the bottom line that describes vacuum state, and from the top to vacuum, when the particle undergoes symmetry breaking, it gains mass, and that is mediated by Higgs boson. So the particle which gives mass for these particles is the Higgs boson. So the assumption is, they assume that this Higgs field is pervading the entire universe. Depending on the interaction, the particle gains the mass. More the mass, so more the interaction, more is the mass, and less of the interaction, less will be the mass. And if there is no interaction, that particle will not have any mass. So that is the theory that was proposed by Peter Higgs and others. Next one, please. So as I said, to discover this, so this lab was dedicated, that is some lab, which is the world's largest laboratory. So the circumference of that lab is about 27 kilometers, that is kept underground, nearly 200 meters down the surface. And here the protons are accelerated almost to the speed of light. 99.99% of the speed of light, and each proton is accelerated nearly for about 7 tera-electron volts, and these protons moving from opposite directions, they made to collide, and during that case the smasher that will produce the temperature which is almost 100,000 times the temperature of the sun, just imagine, but it is only for a small duration. And to take this simulation, more than 3,000 computers are used, and this project was completed in 2008, but the discovery happened very later because people went to court. There is a story behind that. People assume that there will be formation of black holes, and these black holes might eat the complete Earth. They went to court, and the scientists have to go to court, and they have to convince the people, and finally court sanctioned this experiment. And more than 5,000 eminent scientists, particle physicists, were involved in this project. You can call it as a project, greatest experiment of the century. Next one. And this is the Feynman diagram, which explains the production of the Higgs boson. Two protons which are moving in opposite directions, they produce two W particles. They interact to produce Higgs boson only for a short duration, for about 10 power minus 21 seconds, and that immediately decays into Z bosons, which in turn decays into electron and positron and muon and antimuon. Next one. And this is the sketch of that laboratory, that LHC, Large Hadron Collider. There are 4 labs there: CMS, ALICE, ATLAS and LHCb. And there are proton synchrotron, super proton synchrotron, etc. Next one. And this is the aerial view, satellite view of the Sun laboratory. So it is underground. So you can see cities there. It is in near Swiss-France border. Next one. Yeah, so this is the inner view of this laboratory. Next one. See, here protons are accelerated almost to the speed of light, and you have to take them around a circle. So you need to apply huge magnetic field. You know that when a charged particle enters into a magnetic field, it will move in a circular path. So in order to take it in a circular path, you have to apply very strong magnetic field. For that, they use superconducting magnets. And interesting thing is, most of them are supplied from India. That is the interesting thing. So this is a picture of that superconducting magnet. Next one. And finally, that announcement was made, so that brown color, that is the collision of two proton beams, so that produces a Higgs boson momentarily, and it will immediately decay. So it's a resonant particle. From the peak you can understand there is a formation of Higgs particle, and that immediately decays, as I showed in the Feynman diagram. So this announcement was made on 4th July 2012. Next one. Next one please. Next one. And this announcement came from 2 laboratories simultaneously from that LHC. So one is ATLAS, that comprises of 2,800 nearly 3,000 physicists, including graduate students, and nearly it's a collaboration of 169 universities and 37 countries. So these kind of projects cannot be done by one single country. So it's a collaborative work. And the other one is the CMS lab. It is actually very big by size. You can notice there are 2 persons standing there. Here also you can notice 1 person standing there. And CMS lab is a collaboration of more than 49 universities, and 430 students were doing PhD during that time. Next one. Next one. Yeah, this is the computer generated view of Atlas detector. Next one please. Yeah, this is the property of the Higgs boson. So it is a boson basically, which obeys Bose-Einstein statistics, and it is a spin zero particle. And the theory, basic theory, was formulated by Brown, Eckert and Higgs, and later by that Guralnik, Hagen and Kibble. In standard model, there is one Higgs particle. So there is a supersymmetry theory that says at least there should be 5 Higgs particles. So we are going to do a lot of research to find whether it is 1 or 5. And as Kagali sir said, mass of this particle is about 125 GeV per c square. Okay, this is about the properties of this Higgs boson. Next one. Now you can notice that this is the complete periodic table of that elementary particles. I showed it. We have quarks, 6 quarks, 6 leptons, and gauge bosons to mediate these charges, to mediate these forces. They are vector particles, but you know the last one, Higgs boson, is a scalar one. So that is the one which gives mass for all massive particles at the elementary level. Next one. So we too have participated in this project. We are also part of this discovery. India has contributed around 100 crore, particularly in terms of conducting magnets. And the one who can see that you can see that his name is Prabhu Kumar Behera. He was working there in Atlas group, and we spare almost around 100 scientists for this work. Next one. On 14 almost July 4th was the announcement of the discovery, but on 14th December 2012, they said possibly there are 2 Higgs bosons. Both of them are scalar particles, and that was the signature of this existence of these 2 particles, and still the confirmation has to come. So people are doing research on this. Next one. And these are various decay mechanisms. So Higgs particle, so that leaves only for a short duration, about a jeptosecond, 10 power minus 21 seconds. Just imagine 10 power minus 21 seconds. But we have technology to detect that particle, even if it exists for that small time. And there are various modes by which it decays. Okay, these are different modes with possible errors. Next one. Next one. So there are different Feynman diagrams to explain decay. I am not discussing all those things because, yeah. Okay. So they are saying that there is no time. So I will wind up at the quicker rate. So as Swamiji said in the morning, see, so far there was no God. God came here. That Ian Lederman is a Nobel laureate. Actually, he got Nobel Prize for the Neutrino Oscillations. And he wrote a book on this particle physics. So there actually he named this particle as God-damn particle, as Swamiji said, by assuming that even God cannot find this particle because reaching that energy is not easy. But the publisher, so he just removed the word damn and he just retained God particle. That is why God came here. Other than that, as I know, there is no connection between God and physics, because of that, we are talking about God particle. Otherwise, we would not have talked about God particles. Okay. Next one. So for this work, in 2013, this Englund and Peter Higgs got Nobel Prize. Next one, please. And he is unfortunate because he is one of the founder member who proposed this theory, Brown, but unfortunately died in 2011, just 1 year before the discovery of Higgs particle. Next one. There are various analyses. See, it is not the end of particle physics, it is the beginning. As Kagali sir said, we have to answer for many questions. Whether it is one or many such particles do exist. Why supersymmetric? Whether standard model is really standard, or we have other theories, parallel theories, which is really standard, like supersymmetric model. And he mentioned about dark matter and dark energy. Whatever you see around us, is only about 4%. Visible universe is only about 4%. 96% we don't know anything. Okay, that is non-barrier. So this Higgs boson is a candidate which can answer for this. And in the universe we see only matter. where did this antimatter go? Because you know that as per the concept of pair production, particles and antiparticles are produced in pairs. But where is this antimatter? So these kind of questions are left over unanswered. So there is a lot of scope. So this is the beginning. There is a video of 5 minutes duration which can be played after the second speaker. An abroad speaker is waiting online. So maybe you can take up the questions, and also that video you can watch only at the end. Thank you.
The time is up. If you have any questions with the Dr. TSS, you can discuss after the completion of the speaker from abroad. Over to the next speaker and next chairman. Thank you.
Sri Gurudev. Good afternoon everyone over here. Honorable Chairman, respected Speaker and all the participants. Now we have completed the first technical session of our seminar on discovery of God particle. Go. I welcome M.E. Meghana, Professor of Chemistry. Over to you, ma'am.
This is possible to university and collaborating with IMEC. IMEC is the university mindset. So this is a forensic by all the science and the engineering, organic electronics. So then important production light devices. And to deposit these light emitting devices, I will also discuss ultrasonic spray coating and inkjet printing. Okay, so let's start with light emission. And if we talk about light emission, of course, I indicate here 400 to 700 nanometers. This is, of course, in the visible spectrum. We can also that and that is to why then we talk about luminescence, and luminescence is the emission of light. Substrate that has been heated, and this can be done according to the absorption of photons, so light emission after it has absorbed device, what's different? Well, if we talk about an organic light emitting device, then some of the layers, and more specifically the active layer for sure, is from an organic compound. And so you see here the very basic first organic light emitting device. You have an anode and a cathode, so you have two electrodes, one on a negative potential and the other one on a positive potential. And then you have an active layer in between where, like I explained, the light emitting device, you have holes and electrons that come together, that form an exciton and then form a photon that can be emitted. Of course, if you apply this light emitting device, this organic light emitting device in this form, there's a lot of physics going on, and there's a lot of things that can be improved, and that's what has been researched and improved the last, let's say, 70 years. And up to date, you can think about organic light emitting devices that are integrated in displays. For example, here, showing a display that you can bend. So the main advantage of having organic materials, of course, is the flexibility. You can also think about viewing angle as you talk about light emitting devices, so not organic light emitting devices, but semiconductor one. There, the light emission is in a very small angle. So you have what they call a point source, so a very focused light. Where for organic light emitting devices, they talk about Lambertian radiation, and that means that light goes in all directions. And that means that the devices you make, if you think about displays, but also about lighting, then this has a very broad viewing angle. Very nice to watch. Another example is that if you go to this kind of lighting, that with light emitting devices, so not the organic ones, but the bottom ones you see here, always have to have some kind of distribution plane, such that the light is guided in a homogeneous way, while for organic light emitting devices, because they have this Lambertian radiation pattern, you don't need what they call backlighting, and you don't need this layer on top. So it's thinner, or it can be thinner, it has no backlighting, and it uses less power. And well, we say it's unbreakable because it's organic, and it has a very high contrast in comparison, for example, like light emitting devices, phosphor-based devices. So okay, this is the application. These are the things we're working towards. But of course, it started all with investigation on the material side and combination of different layers, different materials. So let's say the first organic light emitting device by Williams and Schott was in principle the easiest thing you could think about. It's 1970, just an anode, cathode, and an active material in between. And this active material was anthracene. And so they used anthracene as a first material to generate light. What is happening if you look at the physics? So in principle, you have two states. You have your ground state and you have your, let's say, first state. You also have a triplet state, so a singlet state and a triplet state. These are excited states. And what is happening, of course, is that if you do the absorption of the energy, let's say, so the applied potential, you have your electron hole here, and then when it falls back from your singlet state to your ground state, it emits light in the form of fluorescence. Of course, what is also possible is that it goes from your singlet state to your triplet state, and then somewhat later, and this is called intersystem crossing, somewhat later it can go via phosphorescence towards the ground state. If you calculate what is, let's say, percentage of possible radiation, so fluorescence is 25%, phosphorescence is around 75%. And in the first organic light emitting devices, the only light emission that occurred was fluorescence. So 25% of the energy you put in is finally coming out. So you do not have very high efficiencies, not very high light emission, but of course, looking into new materials and new build-ups, new layer stacks, this improved over the years. And the first next step, let's say, 1987, was the two-layer organic light emitting device from TAN. So you have your glass substrate, then they put the anode, so this was indium tin oxide, it's a transparent conductive material. Then they put diamine as some kind of hole transport layer, so it helped getting holes from the anode towards the active material. Then you have ALQ3, which is the active material, that's where the photon generation and emission happens. And then you have an electron blocking layer, and finally your cathode, where you apply in principle your negative potential. So this, if you see here, you have your anode on one side, you have your cathode on the other side, and of course there's a difference in work function. So what happens by putting layers in between, if you only put, let's say, the active material, then it will be very difficult for electrons and holes to travel there, because the jump they have to take from one material to the other one, and the energy they need to jump from one material to the other one to overcome the interface, that's quite high. So that's why they put this, what they call hole transport and electron transport layers in between, to ease or to smoothen the way electrons and holes can travel through the different layers towards each other. And then of course, when they meet each other here, you have the hole and you have the electron. When they meet each other, they form an exciton, and when the exciton relaxes, it generates light. So here we go already to quite high external quantum efficiencies. Talk about 1% of photons emitted per electron that you put in, so that's still quite low, because I talked about fluorescence of 25%, here we go to 1%. We talk about the luminous efficacy for 1.5 what? And around, let's say, conjugated water inside active material. So you have again 3-layer stack, but then the active material of the conjugated polymer, the PPV polymer, where of course the nice thing is that you can start playing with these lowest occupied molecular orbitals and the highest occupied molecular orbitals. Quantum efficiency back then with this PPV material was quite low, 0.05%, but of course the same way that we did in the previous materials, we can also inject several layers to ease the transport of electrons and holes. And so the hole transport and the electron transport layer. In this case with Shun, it was carbazole on the hole transport side and PPT on the side. And then you see, if you look at these, let's say, energy levels, you see that it makes it easier. Jumping from 4.8 to 3.7 and 5 is a big jump. But if you put this PVT in between 3.9 electrons, helps the electron to move easily towards the PPV. And the same goes on this side. If you look at the whole side, you can easily go via this carbazole 6.1 electron volts to the PGV. So that's interesting. What also is interesting is for example, here is 6.4 electron volts for the PVD. On let's say the hole side, that means that the hole that arrives at the aluminum electrode. So this, let's say, PVD is not only a transporting layer, but it can also act as what they call the hole blocking layer, such that now you have your holes and electrons generated or stuck inside the PVD, such that they can easily find each other for an exciton and generate light. And so here you see that due to this optimize the stack, you go to quantum efficiency of 2.5%, and you increase already quite a lot. And then what they integrated is even more layers, an extra hole blocking layer, an extra electron blocking layer, and then let's say 1.1 joule per watt, which is a lot less than inorganic light emitting devices. But of course, by optimizing the layers, what happens in the last 20 years, you can achieve it. So if you look at the total stack, and you have your glass substrate, which is transparent, where you have your light emission. You have your anode. This is also transparent and a conductive material. And then you have 3 layers that sometimes are combined, one or two materials, which is your whole injection layer. So it makes it easier for the holes to be ejected from the anode inside this material. Then you have the whole transport layer, easing the transport of these holes. And then the electron blocking layer, such that any electrons coming from the other side will be blocked and will not move further than the active material, which is the emission layer. And then on the cathode side, in principle, you have the same. Your cathode is your high conductive electrode. This is not transparent, not always transparent. And then you have your electron injection and your electron transport layer, and also a hole blocking layer. So this is a complete stack of an organic light emitting device. But if you think about having all of these different layers on top of each other, of course it's important that these are put on top of each other in a very clean, specific way. And if you look at luminous efficacies, we said that in the beginning, 1999, showed it in the previous slide, we were below this 1 lumen per watt, where LEDs were already like 30 lumen per watt. But you see that all LEDs now in laboratory and then also commercially available are reaching more than 100 lumen per watt. So the target there is reaching the same as the light. I mentioned that putting all of those several layers on top of each other, you need a clean room technology, very expensive. As you think about using polymers, it would be interesting to move away from this clean room technology and see if you can deposit in a different way using what they call solution processing. And that's exactly what we are doing in the lab. So that's what I would like to talk to you today about. Such that we can also, in a more inexpensive way, also put light emitting. So this is the system we use. It's a spray coater, ultrasonic spray coater. That's one of the systems we use in our lab. And you can see a short movie about this. So what you see here is that you have a nozzle and you generate droplets that are then deposited via a nitrogen shroud onto your substrate. I will introduce that a bit more. So what you see here, this is the nozzle head. So you have your ink here. For example, this is a solvent where in principle you can put a polymer or you can put nanoparticles. And then it goes to the nozzle plate, and below here you see the nozzle plate. And on the nozzle plate you have a vibrating surface. And this vibrating surface, ultrasonic vibrations, 120 kilohertz, this generates standing waves, and due to adding more and more energy into these standing waves, at a certain moment there are some droplets that split. And the nice thing about these droplets is that these droplets have specific size, a specific concentration, let's say composition that is for all droplets more or less the same. And also these droplets have nearly no kinetic energy. So what we do then, what you see below here, is that you take nitrogen and you guide these droplets towards the substrate. So with the nitrogen pressure, you can apply high speed or lower speed to the droplets, which can be interesting for specific applications. So in here you see the final device, the organic light emitting device that is spray coated. But how we get there, that I will explain in this part. So I will move to explaining more specifically the active material, which we use is super yellow for the light emission. So I talked already about this ultrasonic spray coating, and one of the questions we had is, well, this ultrasonic spray coating, this generates by ultrasonic vibration these droplets. But of course, if there's a polymer inside the liquid, what will happen with the polymer because of those vibrations, this ultrasound? Maybe this polymer will be cleaved. So that is one of the things we investigate. So here you see the material we use for the experiments. This is our PPV material, super yellow, which is the material that emits light around, let's say, I think 550 nanometers. And what we wanted to see is if we do this ultrasonic vibration, if our polymer will maybe be seized at the backbone, or maybe that you have some side change that would be cleaved. So that is something that we investigated. How we did that? Well, we took our super yellow, we spray coated it, and then with the ultrasonic spray coated solution, we made organic light emitting devices with spin coating, and we compared that with normally spin coated devices. And here you see the pristine solution, here you see the ultrasonic atomized solution, and if you look at the absorption spectra, they more or less overlap. So based on that, we said, okay, based on only this experiment, we can say that there's no real change. But of course, you need to dive deeper. You need to really go into chemical analysis of your polymer. That's what we did with GPC, so gel permeation chromatography. And also there you see that the molar mass did not really change and changed a small bit to the higher side, which is strange for the ultrasonic atomized solution. So based on that, we also decided the length of the polymer, so there's no backbone scission, and the length of the polymer stays intact. Of course, if you want to know what is happening with the side change, if they will change, then one thing you can do is using FDIR, so the Fourier transform infrared spectroscopy. And also there we compared the pristine solution with the ultrasonic atomized solution, as you can see here, and also all those peak coincidence, so there's no real difference. We did the same with NMR, using this nuclear magnetic resonance spectra, and there also we don't really see quite big differences in chemical shifts. So based on this, we could evaluate that ultrasonic spray coating is a system that can be used to deposit polymer material without destroying or degrading the polymer material. So then the next step, of course, is that you investigate layer formation, and that's of course what we did. We took the super yellow and we spray coated it, and we compared that with spin coating. So on the left side, you see a spin-coated sample studied by atomic force microscopy. This is an area of 10 by 10 micrometers, and if you measure the RMS roughness, this for the spin-coated one is around 1.2 nanometers, which is really smooth. But of course, you need to have it that smooth because the total thickness of the super yellow layer inside the organic light emitting device is only around 80 nanometers, so 80 nanometers. So having a very low roughness is really needed. If we look at spray coating, then we see some white areas. These are white clusters of material. But if you compare the RMS roughness, we are still quite low. And the highest peaks go to 4.6 nanometers. And in the total thickness of 80 nanometers, this is quite okay. And the RMS roughness reaches nearly 2.8 nanometers. So based on this, we could say, okay, we can deposit very nice ultrasonic spray coated thin films. But of course, it's important to reach this 80 nanometers and to reach the lowest roughness as possible. So that means we play with different parameters of the spray coatings. I'll show a few of those. The first one is the nozzle flow rate. That means how much of material do you deposit per second or per minute out of the nozzle. So that's the amount of material that you deposit on a specific area. Then of course you have the solution concentration that's more related to the ink formulation. How much weight percent of polymer do you put in your solvent? And then the last one is the nozzle speed. So you saw in the movie earlier that the ultrasonic nozzle can move around. And of course, the faster it goes, the less material per area you can deposit. So this is what we played with. Here we looked at the constant speed of the nozzle at 15 millimeters per second, so 15 millimeters per second. And we looked at the influence of the flow rate and the concentration on the layer thickness. So we measured the layer thickness, and you can see that if you have a constant speed of 15 millimeters per second, that this 80 nanometer is reached around 1.6 milliliters per minute, so the flow rate having 1.6 milliliters per minute deposited. And the concentration, if we would like to go to 80 nanometers, you should go somewhere between 2.5 to 3 milligrams per liter. So let's take this constant flow rate at 1.5 milliliters per minute and play a bit with the speed to see what happens there. What you can see, of course, the faster you go and the less material is deposited per area. So based on this, we could say, okay, if we want to go to 80 nanometers, we should be around 13 to 14 millimeters per second. So based on this, we have optimized all the parameters of the ultrasonic spray coating system to get 80 nanometer thick layers, very smooth, around 2 to 3 nanometers. And we investigated that the material that was ultrasonically spray coated was not degraded. And so based on this, we have deposited one of the layers of the organic light emitting device and then put that in an organic light emitting device in total and measured the light properties. So here you see the organic light emitting device, and we measured first the current voltage characteristic, so the IV or the GV characteristic, where we see that one for the spray coated one. And here, this is the luminous power efficacy, so the amount of light per power that you put in the device. And here we can see we go to 10, at a driving voltage of 4 volts, we go around 10 lumen per watt. If you remember from the introduction, there I said that in the beginning, around 2000, you had introduced polymer material reaching 1.1 lumen per watt. So you see with the super yellow we reach 10 lumen per watt. But there are materials in research that already can go to 100 and a bit more lumen per watt. But super yellow is what we call a workhorse material, something to organize and to test and to research, but not the highest quality and not the highest luminous efficacies can be reached. Okay, so to conclude this part of the story, the polymer molecular structure remains intact. We have showed that we can deposit uniform active material, also uniform organic light emitting devices, and we reached luminous efficacies around 10 lumen per watt. And the interesting thing is that this ultrasonic spray coating is in ambient conditions. So if you compare that to the clean room environment, this ultrasonic spray coating is a cheap, very price positive device that can be used in ambient conditions and still reach quite nice results. So and then of course what we are doing in the research is optimizing all of those layers so that we can come to a fully printed stack, that we don't need this vacuum deposition. For example, we are removing the calcium, one of the electron transport or the electron injection layer also by polymers. And one of the things you would like to do is also to use transparent components, and therefore we use inkjet. So if you look at the stack, here, this normally is indium tin oxide, and indium tin oxide is, of course, it's transparent, but it's also deposited by vacuum deposition. And we were thinking, okay, if we can replace this indium tin oxide by a transparent conductive material, and the conductive material is silver, but silver, of course, is not transparent if you print it relatively thick, 150 to 250 nanometers. So then the question is, well, maybe we should make a grid such that we still have transparency. That's what we did. We started with thermal evaporation of calcium aluminum. So we let's say turned the stack. So we started with the top layer, aluminum, calcium, and we go from top to bottom. So calcium, aluminum was evaporated. Then on top we put the silver contact, and we compared the silver grids with the gold grids. So if you go for gold, what you can do is you use thermal evaporation, but you can go very, very thin. If you go to 1 to 50 nanometer, the gold is semi-transparent. You see the top layer here, the gold layer, this is quite transparent. And the sheet resistance goes from 3.2 to 123 ohms per square, which is also in the range of material that we need in transparency compared to the utilities. Transparency is going 25 to 70%. But of course, if you go to inkjet printing of these grids, what you see here, we reach layer thicknesses of 150 to 250 nanometers, but we reach a sheet resistance of around a few ohms per square, compared here to this one, which goes to 100 ohms per square. So the sheet resistance of this inkjet printed layers is much, much better than the gold layers. And also transparency, because you only have, let's say, a full blocking when you have the printed silver line, but the rest is still perfectly open. So depending on the coverage, depending on the design that you choose, you go to a transparency of 70 to 90%. And so here you see the transmittance and the blue lines. These are the hexagons and the designs of the silver grids, while the yellow lines are the transparencies of the gold. And you see that, of course, when you have a very thin layer of gold, 1 nanometer, 2.5 nanometer, then you can reach a very high transparency. But if you compare that to your sheet resistance, then you go much higher than mega ohms. Of course, that's not enough for this injection of and distribution of your holes. So that's why if you compare and take the best combination, going to silver grids, having very good sheet resistances and very high transparencies, could let's say replace the indium tin oxide. And that's how we evolve. So we take substrate, we put our electrode, which can be these silver grids, but we're now moving also to silver nanowires combined in the BOPSS, because this can be fully spray coated as well, so we can replace the inkjet printing by spray coating. The super yellow I showed we can easily deposit by spray coating, and I also said that the calcium, so one of the layers in the typical stack, we are investigating to be replaced by polyethyleneamine. And finally, we need to put one electrode on top, which, for example, has fully spray coated organic light emitting device on a flexible foil, so you see you can flex it a bit, and it still has very nice light emission. So with this, I would like to thank you for your attention. I would like to thank all of my colleagues and the PhD students, and the postdocs, and the researchers, and the ones in bold here. Inge Verhoeven, Rachid, and Koen Gielis are the ones that worked on the organic light emitting devices and provided all the results and the nice figures that I showed in this presentation. So with this, thanks for the chance to give the presentation.
Chairperson of this technical session. The chairperson of this technical session, Dr. Prasad, Dean, School of Natural Sciences, Adichunchanagiri University, to sum up the entire session. Over to you, sir.
Jai Sri Gurudev. So our text today is to thank Dr. Wendy from Assault University of Belgium. I think we touched upon the points starting from flexible organic light emitting diodes to transparent light emitting diodes using conjugated polymers to metal ions and also using inkjet printing or 3D printing. And he started from simple structure and ended up with a complex structure. I think if you observed this presentation, he started with 2-layer light emitting diodes with anode, cathode and active material. At the end, there is so much of flexibility and so much of transparency in complex structure. I think I request everyone to join me in thanking Dr. Bindi for me for giving a wonderful lecture on organic light emitting diodes. Thank you, Dr. Bindi for me. And now the session is open for discussion. If there are any questions, can you take some questions? Hello, can you hear me?
I can hear you, but it's not that easy.
Okay. So if there are any questions, then I will tell you. So any questions from the audience side? No. Okay, I have one question which is very general. What about the electronic waste? So it's very nice to use laptops, computers, and then mobile phones, gadgets, whatnot. So what about the electronic waste? How the European Union tackling the electronic waste problem? Because in India we are seeing mobile phones thrown in the streets and in the dustbins and everywhere. So do you have any ideas or do you have any inputs to give regarding the electronic waste?
Sorry, very difficult for me to understand the question.
Okay.
I'm sorry for that.
Okay, no problem. Can I ask now? Can I ask?
I can hear something, but I cannot really specifically hear what you're saying.
Okay, so I was asking you about the electronic waste management in European Union.
Did you mention something about European funds?
European Union electronic waste management system.
Sorry, I cannot hear you.
Okay, so if possible, can you please start?
Yeah, that would be interesting. Type of question.
Yeah, can you please start in the part? Thank you so much for your presence, and it was a great honor for us, and it was, thank you for enlightening us on organic light emitting there. Thank you once again. Thank you, Ananda.
For this technical session, I am very obliged to thank Dr. Prasad, Chairperson of this technical session, Dean, School of Natural Sciences, Adichunchanagiri University. Thank you, sir. Thank you for your gracious presence. I would like to thank Speaker of this session, Dr. Dept, Professor, Hasselt University, Belgium. Thank you for the informative session, sir. And Rapporteur, Professor Naveria Banu Madam. Thank you, ma'am.
It's time for lunch. I request all the guests to join for the lunch. It's been arranged outside. At exactly 2:30, we will be commencing with the paper presentation session 1. And one more announcement. The participants, those who have not registered and those who have not completed the process of registration, so kindly complete the registration process in the registration counter. Thank you.